Okay, so we are now on Unit 5. We have 2 units left after this one. We are going to be talking about rotation. So we did a little bit of this last year if you were in AP Physics 1. But we're going to do some review first, and then we will go from there. So this first page, you can find a link to this AP Physics Chapter 11-12 Key Equations and Ideas. We're going to be talking about some basic velocity and angular velocity, acceleration and angular acceleration. We are going to start looking at integrals now. We're also going to be talking about kinetic energy for rotation. We're going to revisit centripetal acceleration. We're going to do a new topic called the parallel axis theorem, and of course we're going to revisit our kinematic equations, but now for rotational motion. And then we have it divvied up down here. We're also going to talk about torque, angular momentum, and rotational work and kinetic energy. Okay. Underneath these equations, you can find your key ideas. So all of the things you need to know to be successful in this unit. I do not know why my second page did not. Oh, maybe there wasn't one. No, there is one. There should have been a second page of that. Okay, right here. So this is your second page of all of the information you need to know for the Unit 5 rotation, okay? Also included in here is this table of rotational inertias. So all of these equations here pertain to specific objects. So I will go into more of what that inertia is and talk about these. You do not have to memorize these. Usually if you need it for the AP test, it will either be given information or you will have to derive it using calculus. And I will have a video showing you how to derive these rotational inertias. That is where they come from for these objects. Okay, that'll be in a different video. What we're going to start off with in this one is the comparison of linear and angular motion equations. So we did some of this last year. You probably recognize the table because we filled it out last year if you were in AP Physics 1. So let's talk about these, okay? So linear is what we've done all along. It's what we did all through last year for AP Physics 1. So I'm going to go ahead and fill out the linear equations, and then we'll go back and talk about the angular equations. Okay, so here are all of our linear equations for all of these quantities. Work is listed twice down at the bottom, as well as force, because we have some calculus pieces that we tied in here. So displacement, of course, is just the final position minus the initial position. Velocity is the derivative of position with respect to time. Acceleration is the derivative of velocity with respect to time. And then we had our kinematic equations. Please note this one is not on the equation chart, but it is helpful sometimes. So the should be the displacement. Can be found with 1/2 of the final velocity plus the initial velocity times time. Net force, of course, is mass times acceleration. Kinetic energy is 1/2 mv squared. Work is force times distance. If there's an angle, then you got to add in the cosine of theta. The spring force is the negative spring constant times the stretch or compression of the spring. Elastic potential energy is 1/2 the spring constant times the stretch or compression of the spring squared. Remember, this is stretch or compression of the spring, not the distance the object travels. Momentum is mass times velocity. Conservation of momentum says that the initial and final momentums have to be equal to each other. Force is equal to the derivative of momentum with respect to time. That was when we went and talked about impulse. Okay, so think about that. And then work can also be the integral of force with respect to distance or displacement. And then power is force times velocity. Okay, so let's talk about the angular equations that go along with these, or the angular analogs. So for displacement, this should have a delta in front of it. For displacement, we use theta, and it's just the final theta minus the initial theta, okay? That is displacement, angular displacement. Angular velocity, we use omega, and it's equal to the derivative of the angular displacement, which is theta with respect to time. And the acceleration, which we use alpha, looks kind of like a Jesus fish. That is the derivative of the angular velocity with respect to time. So notice the equations are really similar. They just have the angular variables in there instead of the linear ones. So angular velocity at any point is equal to the initial angular velocity plus the angular acceleration times time. The angular displacement is equal to the initial angular velocity times time plus 1/2 the angular acceleration times time squared. The angular velocity at any point is equal to the angular velocity squared. Initial angular velocity squared plus 2 times the alpha and the displacement, angular displacement. And then that equation that's not on the equation chart. I'm sorry, I have a hard time writing small with my stylus. Okay, so there are your angular kinematic equations. Force is really similar. Again, it's the same kind of thing. Except for now, the force is equal to, we don't use force. It's called torque now. And torque is tau, which is the T with the curly on top. And it's equal to rotational inertia times the angular acceleration. And we'll talk about that in a minute. Rotational kinetic energy and these other things we will talk about next time because you don't need those for today. Okay, so there is a connection between these, and we talked about some of these last year. The linear displacement can be found by taking the angular displacement and multiplying by the radius. So let's go ahead and put R's radius up there. The linear velocity can be found by taking the angular velocity and multiplying it by the radius. The linear acceleration can be found by taking the angular acceleration and multiplying it by the radius. Be really careful with the kinematic equations because those you can't mix them, okay? So you have to be careful when you're doing those. And then torque, of course, is going to be the force times the radius, and we'll talk about that one some more when we talk about torque, okay? At the bottom, the arc length, all right? So we're talking about on a circle. If we're talking about the arc length, we're talking about a piece of the circle like that. It is designated with an S, and it equals theta times the radius. It's really similar to the linear displacement along that part of the circle, which is why it's similar to our equation, how we can go from our angular displacement to our linear displacement, okay? Linear speed, we just did that up there. It's the angular velocity times radius. And then linear tangential acceleration is the angular acceleration times the radius. Okay, radial acceleration, we called it centripetal acceleration. So they are equivalent. It's v squared over r, but now since v could also be equal to w or angular velocity times the radius, we can also write it as angular velocity times the radius. And then the period can be found Remember that the period is the time for one revolution or one time around the circular path. And we use a capital T. We can find that by taking the circumference of the circle and dividing it by the linear velocity, or we can take 2 pi divided by the angular velocity. Okay, so let's review some basics from rotational motion. All right, so just to review, again, our variables, the angular displacement is represented by theta. So if it's displacement, we do delta theta, and we just did the equation for that a minute ago. Angular velocity or speed is the omega, which looks like a W, and then angular acceleration is alpha. Okay, and then the units for these are radians or rads. Ooh, I don't know why my pencil does not want to write. Or radians per second, or radians each second for omega. And then radians each second, or radians each second squared. And like I mentioned before, the biggest thing is making sure you don't mix linear and angular quantities together. Okay, last year we talked about the unit circle. So we're revisiting that. So when we're talking about displacement in radians, we are talking about pi. Okay, so if I start here, I have 0 radians. If I come back over here, I have 2 pi radians. That's why when you do the circumference of something, it's 2 pi times the radius, because the distance around the circle once is 2 pi radians, okay? So then over here is pi radians, so halfway around a circle. That means this one is pi over 2 radians, and this one is 3 pi over 2, okay? We can also look at the circle in degrees. So this part would be 0 and 360 degrees. Then I have 90 degrees. I have 180 degrees and 270 degrees. That means 1 pi rads or radians equals 180 degrees. So you're going to need that conversion factor because the practice problems for today have you converting between radians and degrees, okay? If we're going into linear, then that's when you have to use the radius. So we can think of the circumference of the circle in different ways. It's 360 degrees. It is 2 pi radians, or it's 2 pi r, and usually we do that in meters, okay? So this would be in degree mode. This is in radian mode, or our angular mode, and this is linear. Okay, the rest of the practice for today basically has you just looking at centripetal or radial acceleration, okay? So AC is the same as AR, so if it's AC, they'll mention it as centripetal acceleration. This one's radial acceleration. And then there's tangential acceleration. And so let's just look at what those mean as we look at a circle. So there's a couple of things that go on with our circle, okay? You could have what we call the arc length S We also refer to that as our tangential displacement or our linear displacement. And then we have these different accelerations. So our radial acceleration would go towards the center. If this was an object moving counterclockwise, it would have a tangential acceleration in that direction. And then it has an overall direction, which we get by just doing the vector addition. So that's my tangential. This is my radial. Remember when we do add vectors, we add them head to tail. So I would move my radial acceleration over here so I could do head to tail. Let me move this one out of the way. That means I get an overall acceleration in this direction. Okay, so those add together for an overall net force or an overall acceleration. Last year we treated them as two different things. Sometimes we will do that this year, sometimes we won't. It's just going to depend on what the problem is asking you. So you need to always look for your context clues there. Okay, so use this information, use the information from the table that we filled out, and that will help you with the practice problems for today. It's a lot of review over centripetal acceleration and net force for objects moving in a circle, okay? So just to recap, centripetal acceleration can be found with v squared over r or w squared times r, and then that net centripetal force would be mv squared over r, or the angular velocity squared times the radius, okay? So you're going to need those for today, and they're also going to ask you about the relationships between linear and rotational motion. I will do a quick video explaining at least some of the problems, and I will get it posted for you by Friday. There will be a basics quiz on Friday over the practice, so be ready for that. It will be multiple choice. And again, if you have questions, let me know, or join a Zoom or whatever works best for you guys. Okay? Have a great day.